Okay, let's talk cycling power. So remember, power is rate of work done, units of watts, and conceptually, power tells us how fast we're transforming energy from one form to another. When we're dealing with human performance, we're talking about transforming chemical energy to mechanical energy. All right, so we'll get into that a little bit more. Let's see how power, rate of work done, lines up with our kinetic analysis. Now, you should have already watched the kinetic analysis video, and we derived this equation here from F equals ma. We add up all the forces acting on an object. That equals the product of mass times acceleration and center mass. Again, mass is the bike rider system together, and that's the acceleration of the center mass of the bike rider system together. Now, we're only going to concern ourselves with horizontal movement right now, not vertical, okay? So we only add up the forces acting in the horizontal direction. That's a Z in the horizontal direction. And the forces acting on the bike rider in the horizontal direction include propulsion force, rolling resistance, slope, drag. These are negative forces, indicating they are opposing the direction of movement of the cyclist. We add up all these forces, and when that gives us mass times acceleration. Now, remember, slope force, we're dealing as a resistance force here because we're going to be looking at biking uphill. If we were biking downhill, this would be a positive force, and that would be acting in the same direction as the bike going downhill. If we're dealing with drag force, what we're dealing with it as a resistance force, meaning the wind is hitting the front part of the cyclist. If there was a strong tailwind, this could be a positive force, and that would aid moving forward for the bike rider. But for now, we're going to call these resistance forces. In fact, where's power? Power is not here. Well, remember, power, let me write it out here now, equals work over time. And remember, work is application of a force over some distance. So if I put FD in the power equation, maybe you can see F and D over delta T, this right here is velocity. So power, another way to write the equation, is force times velocity. So we have one equation, we have two equations for power. They mean the same exact thing. They have the same set of units, watts, or just W. Okay, two different equations, force times velocity. This says power is equal to the product of force and how fast that force is being applied. This is telling us power is equal to rate of work done. They mean the exact same thing, both how quickly we're transforming energy from one state to another. All right, so, but power is not here in this equation. Nowhere there's power. So I'm going to do a little trick. A little piece of paper. And I'm going to rewrite that equation here, F propulsion minus rolling resistance minus slope resistance minus drag force equals MACOM. Actually, what I'm going to do is I'm going to take this equation and I'm going to add all of these to the other side of the equation. I'm going to move them all over to the other side of the equality sign. So I'm going to rewrite this as F propulsion equals MACOM plus, now I'm going to add FRR plus F slope plus F drag. So I'm just doing my algebra to move this to the other side of the equality. I add FRR over here. Whatever I do to the left-hand side of the equation, I need to do the same thing to the right-hand side. So adding FRR over to the other side of the equation. I get this new equation right here. I still don't have power. So where's power? Well, what I'm going to do, here's the trick, is I'm going to multiply both sides of the equation by the velocity of the bike rider. Multiply both sides of equation by velocity of bike rider. How fast a cyclist is going, okay? This is the trick, if you will. So let me do that. I'm going to take V times F propulsion equals, and I'm going to put this all in brackets now, AMACOM plus FRR plus F slope plus F drag times V. Look at this. This right here, this is force times velocity. This is power. Force times velocity. Force times velocity. And now power is equal to all of this over here. MACOM plus FRR plus F slope plus F drag times how fast the cyclist is going. All right. Now, this equation is fine the way it is, but and we can use this and talk about it the way it's set up. This is what the cyclist is doing. This is what the muscular action, this is what the pushing on the pedals is all about, generating power, taking chemical energy in the body and converting it to mechanical energy. This is what the person does. Okay, this is what the cyclist does. The cyclist generates power. The amount of power a cyclist generates is such that he or she can cause acceleration of the bike, can cause a rate of change of velocity. Or another way of looking at this is the power necessary to move the bike forward has to overcome rolling resistance, slope resistance, and drag resistance forces. Okay, let me take this a step further just so you can see it. This is really the basis for how to improve cycling ability. Let's take, for example, e.g., cycling at constant velocity, which is probably what you're trying to do mostly when you're doing a long distance bike ride, 112 miles, 40 kilometers, whatever it is. You're trying to maintain a constant velocity over that distance. If velocity is constant, then you know from your biomechanics, acceleration is 0 meters per second squared. That's a nice number, because if we take that 0 meters per second squared and put it into this equation, I can make this even simpler. So now I'm going to put power equals FR rolling resistance, F slope, F drag, times how fast the cyclist is going. Now I can see a little bit more. The power that the cyclist is generating is equal to all the resistance forces times how fast the cyclist is going. I'll write it one more way. This is just algebra. It's just manipulating the equation. But how fast the cyclist is going, I'm going to put on the left-hand side of the equation, is equal to how much power the cyclist is generating divided by all all the resistance forces. So let's think about this, or let's look at this equation. The power that I can generate as a cyclist, it's a known quantity at any moment in time. Let's say it's 200 watts. That's how much I can generate. That's how hard, that's how much force I can push on the pedal and how fast that force is being applied. That's power, all right? If I can generate 200 watts, in order to go faster, I need this denominator to be as small as possible. That means I need very little rolling resistance, as little slope resistance, and as little drag resistance as possible. The smaller I make the denominator for given power, the faster I'll be able to ride. How do I reduce rolling resistance? I buy good tires. I choose the right tire pressure. I choose the right wheel set. How do I reduce slope? I reduce the weight of the bike rider system, or maybe I choose courses that don't have hills. How do I reduce drag force? I wear an aero helmet. I wear tight-fitting clothes. I have a good position that's that a low CDA. I have good bike frame, a good wheel set to reduce drag resistance force as much as possible. The more I can reduce these denominators, these numbers in the lower part of the fraction, for given power, I can go faster. So what's the secret to going faster? One, reduce resistance forces. So how to go faster? There are two ways. One, decrease the denominator in this equation. Decrease resistance forces. What's the other way to go faster? How do you make this number bigger? Increase power. Train to increase power. Train to convert chemical energy to mechanical energy faster. So instead of being able to sustain 200 watts, maybe I can train and I can sustain 220 watts over 100 miles. Now for a given set of resistance forces, that 220 watts will yield a faster bike velocity. 2, how to go faster? Increase train power. Remember, the power is what the cyclist is doing. So thinking like a biomechanist, you always want to come up with an equation to answer a question. How do I go faster as a cyclist? I either increase the numerator or decrease the denominator in order to make this V as big as possible. So either train hard to increase my physiology and my technique of pedaling so I can have a greater amount of power, or decrease all the resistance forces. And obviously you want to do both. I want to purchase better tires, know how to reduce rolling resistance, reduce my weight of my bike frame and my equipment, and reduce the drag force. All right, so that's cycling power. Thanks, everybody.